मैं राजवीर सिंह शेरान, Associate Professor in Chemistry, SRR Morarka Government PG College, Jhunjhunu. First of all, good afternoon to all the students of MSc Final Chemistry. In the previous video lecture, we discussed about the cell membrane and transport of ions. Today, we will start the new topic in the same unit, neuroconduction. So first of all, we discuss what is neuroconduction. Nerve impulse is the physicochemical change that is transmitted by the nerve fiber. Transmittance of nerve impulse through nerve fiber is known as neuroconduction. It involves alternation in electrical state and chemical changes like oxygen consumption, carbon dioxide output, heat output, etc. Nerve impulses differ from stimulus in the sense that latter is the external force like electrical, mechanical, or chemical force that set up the nerve impulse. The chemical change in nerve fiber brings about recovery process that follows activity, whereas electrical change in the indicator of development and propagation of nerve impulse, that is neuroconduction. Now we discuss the mechanism of neuroconduction. Surface membrane of nerve cells and its axons separates intracellular fluids and extracellular fluids, both of which differ in ionic concentration and composition. Cytoplasm inside the nerve cell is rich in potassium 110 to 170 milliequivalents per liter, whereas concentration of sodium and chloride ions is low. Reverse is true for extracellular fluids. Resting membrane potential. Measurement of the membrane potential by inserting microelectrodes through cell membrane with respect to second electron in the external fluid medium has shown that interior of neuron is about 50 to 70 millivolts negative with respect to exterior. Thus, cell membrane is polarized. Membrane potential of approximately minus 60 millivolt can be reduced to minus 20 millivolts or less by increasing potassium concentration. However, resting membrane potential remains unaffected by immersing neurons in sodium ions free isotonic solution in place of extracellular fluid that contains 140 to 150 molar sodium ions per liter. Hence, resting cells membrane is impermeable to sodium ions. This initiates sodium pump mechanism by which sodium ions enter the cell actively and are extruded by cellular metabolic process which furnish the required energy. As shown in the graph, we take in the y coordinate resting membrane potential in millivolts and in x coordinate we take potassium ion concentration. So the graph is shown in figure. Because of the effectively impermeability of the resting nerve fiber membrane to sodium ions and due to the presence of non-diffusible proteins and ions, the membrane potential for such a system is known as is given by Nernst equation. This is E is equal to RT upon NF ln K plus yani potassium plus ion concentration upon K ion concentration, where R is gas constant equal to 8.316 joules per degree, T is absolute temperature, N is valency of ions, F is Faraday, that is 96,500 coulombs, ln is natural logarithm. At 18 degree centigrade, the equation gets simplified by E is equal to, by putting the value, we can take E is equal to 58 log 10 K plus ion concentration upon K plus ion initial concentration. If potassium ion concentration is taken as 1 by 30, the membrane potential will be 58 into log 0.03, that is equal to minus 85 millivolt. If the ratio is 1 by 50, resting membrane's potential will be minus 98.6 millivolt. The membrane potential is essential for equalizing inward and outward fluxes of potassium. If K plus I is 30 times of K plus O, the concentration of potassium ion will be 30 times as intense as outside. If potential difference across the membrane is less than 85 millivolt, there will be excess of outward flow of K plus ions until equilibrium potential is reattained. Action potential and impulse propagation. An electrically stimulated nerve propagate the nerve impulse, and conduction of nerve impulse along action is related to action potential. Action potential can be measured after suitable amplification as a potential difference longitudinally spread over nerve fiber. As action potential reaches any point on the axon, the surface at the particular point becomes negatively charged with respect to resting part of the axon. We know that in resting conditions, outer part of membrane is positively charged with respect to the interior of fiber. Till 1938, it was thought that action potential is simple magnification of transient reversible depolarization of membrane, so that the active part of the nerve occupied by impulse at any moment shows zero membrane potential. So we can take the equation as a result of this membrane potential transiently approach the equilibrium potential for sodium ions, which can be expressed as E Na plus is equal to 58 log Na plus the concentration divided by Na plus I, that is 58 log 10 upon 1, that is equal to value of log 10 is 1, so 58 millivolt. Outside negative with respect to inside. Therefore, the electrode in the cell interior records a change in potential from minus 70 millivolt to approximately plus 40 millivolt. This accounts for upstroke of spike excitation, which is about 110 millivolt in height. Increase in sodium ions permeability is extremely short-lived and is immediately followed by the rise in potassium ions permeability, and within 0.3 milliseconds of threshold excitation, potassium ions leave the fiber faster than the sodium ions, and therefore resting membrane potential is restored at the site of excitation and fiber again becomes ready for further excitation. Threshold electrical stimulus initiates a propagated nerve impulse. The conduction of nerve impulse is based upon the passage of action potentially along the axon. Propagation of nerve impulse is effected by the electrical currents which flow between active area of the nerve and the inactive area ahead of the nerve impulse. Hence, passage of nerve impulse is stopped by cooling a short length of nerve fiber. Though action potential does not appear after blocked region, a surface electrode placed few millimeters beyond block reveals that a change of potential occurs in this region too. Thus, action potential arrives at the other side of block. This change of potential, also known as electronic potential, is produced by longitudinal current flow between active area and the region beyond block region. Applications of a brief current across the nerve causes a passive distribution of ions across the membrane, which causes change in membrane potential. Under the influence of cathode, membrane potential is reduced, whereas anode increases it. Current flows outwards at cathode and inwards at anode. Electronic potential is most clearly visible when current is too weak to excite propagation of action potentials. So, the current strength required for local response is defined as threshold. One upstroke of excitation is initiated membrane at that becomes permeable to Na plus ions, and the site immediately hits in the axon membrane because becomes permeable to between points A and B as shown in the figure. Now opposite current in external fluid. This current reduces membrane potential ahead of active region by drawing charge out of membrane capacity. A reduction in potential difference by 20 millivolts results in sudden increase in permeability of B from sodium ions, and interior of axon becomes positive at that point, and a spike excitation potential is again initiated. This sequence is repeated through the length of nerve. Above theory of nerve conduction is supported by the study of velocity of propagation of action potentials when nerves are immersed in different fluids. If nerve cells are immersed in oil, conduction velocity of impulse becomes slow as shown in figure. Due to hike in electrical resistance of external medium, we know current is equal to potential upon resistance. The strength of action current I developed by the given depolarization E is reduced. When the external resistance is increased, results in is decrease in distance in front of active region at which action current can excite. Propagation of nerve impulse within the unmyelinated axon is thus by excitation of successive part of axon by the nerve fiber current. Now we discuss chemical transmission of nerve impulse. A nerve impulse traveling through the different peripheral nerve upon reaching the known myelinated terminal produces characteristic responses like increased or decreased activity of smooth or cardiac muscles, nervous discharge from autonomic galvanic cells, secretion from glands, or concentration of skeletal muscles. There is a gap between these sites and the membrane of nerve terminals. The current is pre-sympathetic nerve terminals is so weak that it cannot excite post-sympathetic membranes directly. So, a membrane with nucleus about sodium plus ion is leading to depolarization. Thus, chemical transmission is amplification of weak pre-sympathetic current to depolarization of post-sympathetic membrane, and thus exciting the action potential resulting in action. The process of chemical transmission was revealed by Loewy in 1921. He found that when fluid from perfused frog heart was applied to other frog heart from vagus nerve, slowing and weakening of contraction was observed in second frog heart. He called the substance from vagus stimulation vagus stuff, which was identified as acetylcholine. Similarly, stimulus from sympathetic nerve supply to the first heart resulted in the acceleration of heart rate and increased the force of concentration of both hearts. The time transmitter was named as accelerostop, and which was identified as noradrenaline. Thus, acetylcholine and noradrenaline are two important neurotransmitters. Characteristics of chemical neurotransmitters: it should be synthesized and stored in neurons, particularly pre-sympathetic terminals. Nerve stimulation should lead to release of substance from nerve terminal. Action of substance on inverted organs must be same as that of nerve stimulation. Drug which antagonizes the action of substance at the postsynaptic membrane block the effects of nerve stimulation. There must be the mechanism for the destruction or removal of proposed transmitter. The drug that affect these mechanisms must influence the response to nerve stimulation. Convergent and cumulative evidence for these transmitters has been established. It has been found that acetylcholine and noradrenaline are chemical transmitters in peripheral nerves. So the following type of peripheral nerves are shown. Postgalenic fibers of chlorogenic nerves, all pregalenic fibers of parasympathetic and sympathetic systems, motor fibers in skeletal muscles, certain postganglionic fibers belonging to autonomic sympathetic system, for example, nerve fibers of sweet glands, as shown in the following chemical formula of acetylcholine and noradrenaline. Thank you.